Earlier in the semester, we learned about the gradient. So I have a function here, t of x, y, z equals x squared plus y squared plus z squared plus 20, and we could write down the gradient, del t. Not a very hard set of partial derivatives to take, but what I realized is that went from a scalar function to having a gradient, which is a vector function. And this is a vector field that over a domain, well, now for every point I get a vector. And in particular, I'm thinking about big T as being a temperature function that gives the temperature in degrees Celsius on the interior of a solid metal ball. And so I could imagine that sphere, and we could make up a radius for it, but for right now we could just think about the radius being r. And now for every point, we plug in x, y, z, and we get the gradient vector, which would always be pointing towards where the temperature was the highest. So in this sphere, if I plug in 0, I'd get out just a point, right? I'd get the 0 vector, but for every other point, I would get out a vector with a length that was always pointing away from the origin and getting longer and longer and longer. Meaning that my solid metal ball was getting hotter the further away from the origin I got, like maybe it was in an oven. And that's an example of what we call a gradient field. In general, if you have a scalar function, fx, y, z, then the associated gradient field is just the vector field formed by taking del f. And maybe we'll call that big F because now I'm thinking of it as a field. And there's a gradient field.